All right, good morning, everybody. Okay, so today's topic is using collections as fields. Now, this is still aggregation and composition. It's just that it's aggregation and composition where the objects that the whole is made out of are now collections, right? So arrays or lists or sets or maps or something like that. And so this turns out to be quite common. So you want to implement a class that has some kind of collection as a field, right? And because the class that you're implementing is an abstraction of something that's made up of one or more objects. Right? So for example, you might have you might implement a class that represents a university, right? A university has a collection of faculties, right? Every faculty has a collection of schools and or departments. Right? If you're implementing a receipt class for some sort of billing system, then you can think of a receipt as being a collection of billable items, right? Or items that are sold. On your cell phone, you've got a contact list. Well, your contact list is just a collection of contacts. Right? This is a lie. It's not from the notes. You might consider, if you're implementing, so in a lot of introductory courses, you end up with this class called student or employee or manager or something like that. They're all very similar. None of them are very good examples because you'd never implement these classes in real life. But you can think of a student. If you're keeping track of students for some reason, you might model the student as having a collection of GPAs, and you might model of GPAs and of courses, right? So they might have a collection of courses as well. The example we're going to use today is a polygonal model. So that's just a three-dimensional model that you might find in a graphics application, so video game, movie, some sort of scientific visualization application. You can think of a polygonal model as just being a collection of triangles. Actually polygons, but it turns out triangles are a lot easier to work with than general polygons. Now the question that arises is what does a collection hold, right? So if you're going to implement an aggregation or a composition, right? If you're implementing a composition, you need to, you remember that you have to make copies of the part objects. So if you have to make a copy of a collection, it's important that you understand what exactly a collection is, right? So conceptually, a collection is an object that holds other objects, right? But that's not exactly true in Java. So in Java, the collection does not actually hold the other objects. What the collection does is it holds references to the objects. So for example, if I make a list of dates, right, and I add 3 dates, or I add 3 date objects to the list, right, what's in the list is not the objects. Right? So if you draw a memory diagram of this piece of code, your list is the list at address 200. So we go here, and we look in the list, right? So we add date 1, date 2, and date 3 to the list, right? If you look in the list, you don't see date objects in the list. Right? What you see are references to date objects. And the reference is the same as the reference that you put into the list. Right? So D1 is the date at address 500, which is not shown on the slide. Right? When you add D1 to the list, right, that just adds the reference 500 to the list. Right? So a collection is actually holds 0 or more references to objects. Right? It doesn't hold the objects themselves. Furthermore, they have to be existing objects. Right? So what does that mean? That means if you change D1, right, you ask the list for its first date, right? The list will also have the first date in the list will be changed. Right? Okay, so for example, I make an array list of points. I add the point P, whose coordinates are 0, 0, to the list. Right? So I make the point P, add it to the list, and then I change the x coordinate of the point to 10. Right? Now I print out P, and then I ask the list for its first point, and I print out that point. Right? So when you print out P, you obviously get 10, 0. Right? So it's got to be one of C or D. Right? Now when you ask the list for its first point, right, and you print out the point, you also get 10, 0. Because the point P, because the list, when you add P to the list, right, you're adding the reference P to the list. Right? So if you change P here, then the object that's in the list, the object that's quote unquote in the list, also changes its coordinates. Right? So the answer here is D, right? P points get 0 is the exact same point as P. Right? They both refer to the exact same point. Just a second here while okay. So I'm just, these are just pictures showing you some more UML diagrams. We're not actually going to look at this student class at all. Now, if you think of a student as being a collection of GPAs, right, then when you draw the UML diagram, right, what you draw is you write student, right? In this case, we're using aggregation, it looks like, right? So a student is an aggregation of 0 or more GPA objects, right? So in other words, what's not here is the collection itself is not here, right? So we don't say that student is an aggregation of a list or student is a composition of a list, right? We say that student is an aggregation of 0 or more GPA objects, right? Similarly here, student is an aggregation of 0 or more courses, right? And not student is an aggregation of a list of courses or student is a composition of a list of courses. Right, so the collection isn't shown here at all in the UML diagram. Now, if you decide that when you implement the student class that you're always going to use a list, right, then you can draw it as student is a composition of a list or student is an aggregation of a list of stuff. Right, but normally you write it as aggregation of the individual objects, not aggregation or composition of the collection. Okay. So the same is true of the polygonal model class. So a polygonal model is just a collection of triangles. So when I draw its UML diagram for this, right, its polygonal model is an aggregation of 0 or more triangles, right? So again, not polygonal model is an aggregation of a collection of triangles, right? Or a polygonal model is not an aggregation of a list of triangles, or a polygonal model is not a composition of a set of triangles, right? You use the individual objects themselves, right? Because that's the relationship that's important. Right? The fact that you're using a list or something else isn't that important, right? The fact that it's made up of a bunch of triangles, that's what's important in this relationship. Right? Now notice a triangle is an aggregation of 3 or more of 3 points, right? So every triangle has 3 points that represents its vertices, and it looks like that's how we're going to represent every triangle. Okay, there's an example of some shaded polygonal models. So this is, notice that everything in the picture looks smooth, right? So the surfaces in the surfaces that are shown in the image, they all look like they're round, right? Unless you look very carefully at the silhouette of the objects, right? So if you look very carefully at the silhouette of the ball, you can see that it's not actually round. It's made of a bunch of line segments, right? If you turn off the shading and just show the triangles, you get this, right? And so this is typical in a modern, well, not even a modern. This is typical in a 3D video game. Right, where the objects are all made up of just a bunch of triangles. Right, some of them are very big, right? So the ground triangles tend to be very large. Right? The fact that everything looks smooth and not made up of a bunch of triangles, that's all just a trick that we play by shading in the triangles in a particular way. I don't know if you can take CIS 454 in engineering. But if you're interested in computer graphics, the computer science course is CIS 454. I don't know if it has a corresponding CMPE code or not. But you'll learn all about how to represent three-dimensional objects and how to shade them in so that they look nice and smooth if you take that course. We're not going to get that far, obviously. It's an entire course in 4th year. Okay, so when I go to implement this class, right, so remember what we're doing? I've got polygonal model, aggregation of a bunch of triangles. So there's my class. I guess it should be public. Now, I have 0 or more triangles, right? So I need some sort of collection to hold the triangles. I'm going to use a list. You could use an array. You could use a map. Probably wouldn't use a set, but you could. You could make up your own data structure to hold the triangles. But for our purposes, it's fine if we just use a list. Right? It's going to use a list of triangles called try. I've got a no-argument constructor that makes an empty model. Right? So what does it have to do? Constructor always initializes the fields. Right? So we initialize try to be a new array list. I've got a method called clear that removes all the triangles from the model. So that's easy, you just clear the list. Right? I have a method called size that returns the number of triangles in the model. So that's easy, you just return the number of elements in the list. Right? So that's a very simple, this is a very simple implementation of the polygonal model. Okay, now here's the problem with collections. So when you use a collection as a field, right, you have to decide ownership issues. Right, so number one, does X actually own or share its collection? Right, if it's going to own its collection, you have to use composition on the collection. Right, if it's going to share its collection, you can use aggregation on its collection. Right, but now you have the problem that the collection holds a bunch of elements, right, or conceptually it holds a bunch of elements. So now you have to decide, right, if X owns its collections, does X also own the objects in the collection? Right, so in our case, we have to decide, does the polygonal model own its list? If it does it also own the triangles in the list? Right, because if it owns the triangles, now you have to copy all the individual triangles. All right, so we're going to start with the easiest first. We're going to say that X shares its collection with other X objects. X shares its collection, so X is willing to share its internal, our polygonal model is willing to share its internal list. Right, so here everything's just going to be straight aggregation. Or association. I guess, yeah, it's going to be straight aggregation. Okay, so if X decides to share its collection, then in the copy constructor, right, you don't make a new collection. Right? In the copy constructor, you just say this dot try equals other dot try. Right? So the copy constructor can simply assign its collection, and that means that the collection for one X object is just an alias for the collection in another X object. Right? And so what does that mean? It means in your copy constructor, right, you just write this try equals other try. Right? You don't make a new list. Right? You just say that whatever list is in this model is the exact same list that's in the other model. Right? For get triangles, right, again, you don't make a copy of the list and return the copy. You just return a reference to your list. Right? So for example, so when you draw the memory diagram for using the copy constructor, so I've got an existing model P1. Right? I'm going to make a copy of that model P2 using the copy constructor. Right? So P1 is the object at address 200, so we go here. Right? We've got a polygonal model object. Inside that polygonal model object, there's a list called try. Right? That list, the list object is at address 700, so we go up here. Right? Inside that list object, there's two references, so it looks like it has two triangles in this, two or more, that's what the dot 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 means. Right? It's got at least two triangles in the list, right? And those objects live here and here. Right? Now P2, right? We made P2 using the copy constructor by copying P1. So P2 is a new object, right? So it's a new polygonal object, new polygonal model object. So it's the object at address 500. Okay. But what's its internal list? Well, it's the exact same list as the other objects, right? So they both point to that list up there, right? If you use P1 to change this list, right, then P2 has a reference to that same list, right? So P2 also sees the change in that list, right? So, for example, P1 has 100 triangles in it. I make a copy of P1 using the copy constructor, right? So P2 is my copy. I then clear model P2. Right? So when you print out the size of P2, you expect to get 0. Right? Now, if this is the way you've implemented the polygonal model class, and you've told everybody that this is the way you're implementing the polygonal model class, then when you print out the size of P1, right, you should also expect to get 0. Right? Because you cleared P2's model, you cleared P2's list of triangles, but it's the exact same list that P1 has. Right? So if you just go back to the picture, right, they're the exact same list. So clearing, using this reference to clear the list, or this reference to clear the list, clears that list. Right? So in other words, the size of that list becomes 0. So it doesn't matter which size you print, they're both going to be 0. Right? So the answer here is A. And that's not, there's nothing wrong with this code. Right? So there's nothing wrong with the fact that you got 0, 0. Right? It's just a consequence of how you decided to implement the polygonal model class. Right? Is that clear to everybody? Okay. So what happens if you decide that, well, this isn't the way I want it to work? right? If I clear model P2, I don't want model P1 to also clear, right? In order for that to work, right, they both need their own list. So if X owns its collection, but it doesn't care about owning the triangles in its collection, then you have to do what's called a shallow copy. Right? So if X owns its collection, but not the objects in the collection, then the copy constructor can perform what's called a shallow copy of the collection. Right? So what's a shallow copy? It means, right, you make a new collection object, but you do not make new copies of the elements in the collection. Right? So what does that mean? It means both collections have references to the same objects, right? But they are separate collections. Okay? So the references in either collection are aliases for references in the other collection. Right? Now the picture doesn't change. So when you draw the UML diagram, it's the same picture. Right? Your polygonal model is still an aggregation of a bunch of triangles. Right? Because you're still willing to share the triangle objects. But you're not willing to share the internal list object. Right? So there is a hard way to make a shallow copy. Right? So the hard way to make a shallow copy is to make your own list. Right? So I'm going to make a copy of dates in this case. Right? So I'm going to make a copy. I make a new empty list. Right? And now I just take every date D in the list that I want to copy. Right? And I just add that date D to the copy. Right? And so what does that do? Well, D is just a reference to a date object in the original list. Right? So when I add D to the copied list, or to the new copy of the list, right, I'm just adding an existing, I'm adding a reference to an existing object into the new copy. Right? So in other words, I'm not making new date objects when I copy the list. New list, the elements that go into the list, they're the same elements that are in the other list. Right? So that's the hard way to do it. You write your own loop. Right? Don't do it that way, just use the copy constructor. Right? So when you use the copy constructor for any list or any set, I guess it's true for maps too. So if you use a map to copy another map, so if you use the map constructor to copy another map, then they all make what are called shallow copies. Right? So if I pass in the list that I want to copy to the copy constructor, right, you get a new list. The elements of the new list are the same elements that are in the other list. Right? And you can do this with a list or a set. List or sets, they have a constructor that take in a general collection. Right? So if dates was a set of dates, this also works. Right? If dates is any list of dates, this also works. Right? So this will take in any collection of objects. Okay, so if I decide that my polygonal model class wants to own its internal collection, does not want to own its triangles, right, then you do what's called a shallow copy. So in the copy constructor, right, when you copy the other model's list of triangles, right, you just call the array list constructor, passing in the other list, right, and then you set that to, and then you set this try to refer to the new list. Right, so you've got a new list object, but no new triangle objects. So with the picture, the memory diagram looks as follows. Right, it's so P1 is that object there. Right, it's got a list that lives up here. Right, now P2 I make using the copy constructor. So there's a new polygonal model object. Right, our constructor makes a new array list. So that list there is different than that list there. Right? You go and look at what's in this list. Right? What's in the list? Well, it's the same references that are in the other list. So if I change that triangle, right? So if I use the first list to get that object and change that triangle, right? Then when you get the first element out of the other list, right? It's the same triangle. Right? So changing any triangle affects both polygonal model objects. Right? By changing a triangle, I mean moving one of the points of the triangle. Right? If you remove that point, right, or sorry, if you remove that triangle, it does not remove the triangle from the other list. right? The lists are independent. Sorry, here we go. Okay, so back to the previous example, right? Have a model P1, make a copy of it using, the copy constructor, right? Clear P2, right? P2 size is definitely 0, right? P1 size does not change in this case, right? Because when I clear P2, right? When I say P2.clear, it clears that list, right? But it doesn't affect the other list. Right? So P1 size is still 100, so now you get B, right? And this is probably the way you want your polygonal model class to behave, right? Probably. All right, any questions there? Right, you've got two independent lists, right? But remember the objects in the list, they're not independent. So if I ask T1, right? So, if I ask P1, so if I ask the first model for its first triangle, right? I ask the second model for its first triangle, right? And now I ask the question, are they the same object, right? So the answer is yes, right? Remember, equals equals means are they the same object, right? So the answer here is true, right? Just look at the picture, right? The first triangle in the first list is the triangle at address 1000, right? First triangle in the second list is also the triangle at address 1000. It's the same triangle, so equals equals returns true. Right? T1 and T2 are also equals, right? So if you use the equals method, you should also get true. And so that's what happens when you decide that you want to own the collection, but not the things in the collection. Now, if you decide that you really want to own the things in the collection, right? You now have a composition of triangles in this case. Right, so if you decide that your polygonal model should be a composition of triangles, you have another problem. Right? So if X owns its collection and the objects in the collection, right, now you have to copy, now you have to perform what's called a deep copy of the collection. So a deep copy of a collection means you make a new collection and you create deep copies of all the elements in the collection. Right? So in this case, that means you have to make a copy of every triangle in the collection. Now, a collection is allowed to hold another collection, right? So you could have a list of lists. So if you want to make a deep copy of a list of lists, right, you have to make a new list, and then you have to deep copy every individual list in the list, right? If you have a list of lists, right, you have to make a copy of the original list, plus a deep copy of every list that's in the original list, plus a deep copy of every list that's in the list of lists, right? And so on and so on and so on. Right? So you kind of want to avoid, generally you want to avoid making lists of lists of lists or lists of sets or something like that. Right? You can go a list of lists, but going much further than that, nesting the lists further or nesting the collections further becomes pretty complicated. Okay, so the references in the copied collection, those are actually references to new objects. So now the picture, the UML diagram, changes, right? A polygonal model is now a composition of 0 or more triangles, right? So in other words, a model owns its own triangles. Okay, so how do you perform a deep copy of a list named dates? So I'm going to make a deep copy of a list of dates, right? Now you have to write the loop. There is no method in Java that lets you make a deep copy of a collection. Right? So to make a deep copy of a list of dates, you make a new list, right? Do not call the copy constructor because that's not going to do what you want it to do. Right? So you make a new empty list, right? And then manually loop over the list, right? Adding the elements of the copied list into the new list. But you don't add the elements, you add a copy of every element. Right? So now I have to copy the objects that are going into the new list as well. Right? And in this situation, you're forced to write a loop. Right? So what does it look like for our polygonal model class? Right? So this try, right? My list equals a new array list, right? And it's empty. Right? Loop over the other model's triangles. Right? Every time in the loop, I add a new copy of the triangle to the list. Right? So what does the picture look like now? So P1 has a list that's up here, right? Inside that list, there's a triangle at address 1000 and a triangle at address 1100. Right? Our copy constructor, so copy constructor makes a new polygonal model object, right? It makes a new list, so that's the list here, right? When it makes the new list, it also makes copies of the objects that were in the other list, right? So notice that, right? In the second list, there's now a triangle. There's the first triangle in the other list is now the triangle at address 2000, right? So it's a different object than the triangle in the other list. Right? The second triangle is the triangle at address 2100, which is a different triangle object compared to the triangle, the second triangle in the first model. Right? And so now you really have two independent, two completely independent models, right? They have their own lists, right? If you modify either list, right, it does not change the other list. If you modify a triangle in one list, it does not affect the corresponding triangle in the second list, right? Oh, there are your other two triangle objects. They're shown on the next slide. Right. Okay, so back to this original example, right? I have a model P1. I make a copy of it using the copy constructor, right? And then I clear the copy, right? The size of the copy is 0. The size of the original model is still 100, right? So in other words, clearing the copy does not affect the original, right? So it's 0, 100. Whoa, what happened here? Okay, second example, right? Ask the first model for its first triangle. Ask the second model for its first triangle. Are they the same triangle? The answer is no, right? They're not the same triangle objects anymore, so that's false, right? Are they equal though? Yes, the answer is yes, they are equal, right? Why are they equal? Because we use the copy constructor to make a copy of every triangle, right? So triangle 1 is equal to triangle 1 in the second model, right? Triangle 2 in the first model is equal to triangle 2 in the second model, and so on and so on, but they're different objects. Right. The picture here, right, so if you look at the memory diagrams, it should make clear what the problem is, or what one of the consequences of using composition is. Right? When you make a copy of the polygonal model object, right, you're now making copies of all the individual triangles. So you're using up a lot more, you're basically doubling the amount of memory. Right? So when I make a copy of P1, I double the amount of memory that's needed because I now have two independent but equal polygonal model objects. Right? So that's what if you use straight up aggregation, right? So this is straight aggregation. So when I make a copy of that first model, the only memory that's required is this. Right? All I need is the memory to hold the object and a reference in that object. Right? That might take up a few bytes of memory. Right? But when you make copies of all the individual triangles, right, you basically double the amount of memory you need. So that's the price of composition. Right? The advantage is you have two completely independent objects, two completely independent polygonal models. Right? Are you willing to pay for that advantage? Are you willing to pay the memory price for that advantage? Maybe, maybe not. Right? It depends on the problem you're trying to solve. For polygonal models, you're probably not willing to pay this price in most cases. Right? It's not uncommon to have models that are, so in a modern graphics game, it's not uncommon to have models that are tens of thousands or hundreds of thousands of triangles. Right? In a scientific application, you might have millions or billions of triangles in your model. Right? So the way Pixar's technology works, when it draws an object, the objects are represented not necessarily using a polygonal model. So they're represented some sort of smooth mathematical description. When it draws when it actually renders the images, the models though, it decomposes the objects into triangles. Pixar's technology makes every triangle smaller than a pixel. So every pixel in your final image is made up of many, many triangles. So it wouldn't be unusual to have literally billions of triangles in a scene. Right. Okay, any questions about using a collection as a field in one of your objects? That's actually assignment number 4 if you haven't started yet. Right, so in assignment 4, you need to make a arbitrary precision binary number. And that means you need an array or a list to hold the digits of the number. In this particular case, you don't have to worry so much about the ownership issues. Well, there's one method where you have to worry about ownership issues, but other than that, you're not really concerned about composition in that assignment. All right, any questions? Okay, so we're done with aggregation and composition, but we're not done with relationships between classes. So aggregation and composition, those are, I guess, so dependency, association, aggregation, composition. Those are some of the simpler relationships between objects. Right? You can have more complicated relationships between objects in most object-oriented programming languages. So, for example, you can have something called an interface, right, which we've already seen in the course. Right, so remember what an interface is? It's just a bunch of methods, right, with no implementation. Right, so an interface is just a specification of the methods that an implementing class must provide. Right? So specification, not implementation. Right? Usually an interface is just one or more method declarations, no method implementations. Right? Newer versions of the language let you have static methods in the interface. Right? So you're allowed to put a static method in an interface, and you're allowed to give it an implementation. There's also these things called default methods, which you are allowed to put into an interface, and you're also allowed to give a definition in the interface. Right? We're going to ignore these two for the time being and just look at the simpler case. Also remember that in Java, an interface is a type. Right? So list is an interface. Right? It's not a class, but I can store an object. Right? So I can store an array list reference in a variable whose type is list. Right? So you can actually use the name of the interface as a type. Right? What can I store in T? I can store any reference to an object that implements the list interface. Right? So I can store a linked list in the reference T. Right? And I can store my list in a reference T as long as my list implements the list interface. Okay, so any class that decides to implement an interface has to implement all the methods that are in the interface. Right? So when we implemented comparable, right, all of our classes had to have a compare_to method, right? Because that's the method that's in the comparable interface. There's an important interface in Java called Iterator. So an iterator is an object that knows how to iterate over a collection of elements or a sequence of values. Right? So in other words, it's an object that encapsulates a for loop. Right? That's literally what an iterator is. If you want to loop over a list or set or a map, right, and you want to remove elements while you're looping over that collection, right, then the only safe way to do that is to use an iterator object. Right? So in other words, if you try to write a for each loop to loop over a list and remove all the elements that are, say, less than 0, that loop will probably eventually fail, and you'll get some strange exception thrown. And that's because removing stuff from a collection while you're, that's because when you remove something from a collection, it can break the iterator. Right? Because the iterator doesn't necessarily know that you've modified the collection that it's looping over. Right? But if you use the iterator directly to loop over the list or set, then you can ask the iterator to remove an element from the list or set. Right? And now the iterator knows that it's removed an element from the list or set, and so now it can correct for the missing element as it continues to look at the rest of the elements. Right, so if you look in the list and set notebooks, they show you how to use an iterator to loop over a collection and remove stuff from the collection as you loop over it. If you write a for each loop in Java, you're actually using an iterator object. Right? You don't have to make one yourself. The language does it for you. Right? So the language actually hides the iterator object from the programmer by having the compiler write all of the necessary code for you. right? So when you write for each string s in a list of strings, you actually end up with an iterator object somewhere. Right? So what does the iterator interface look like? It looks like this. There's a couple of methods here that you don't need to know about right now. So there's a method called hasNext, and there's a method called next. Right? So hasNext returns true if there are more elements to visit in the collection. Right? So you have a list of, say, size 10. Right? You're iterating over the list using the iterator. Right? You're not at the end of the list yet. hasNext will return true. Right? When you hit the end of the list, so in other words, when you visit the last element in the list, hasNext will return false. Right? If hasNext returns true, you can call next. Right? So next returns the next element in the sequence. Right? So make an iterator, call next the first time, that gives you back the first element in the sequence. Right? Call it a second time, that gives you the second element. Call it a third time, that gives you the third element, and so on and so on and so forth. Right? If you call next and there are no elements in the sequence, you get an exception. So why is the iterator, the iterator. So that's the iterator interface. Okay. There is a closely related interface called iterable. Right? So an iterable object is any object for which you can write a for each loop. Right? So list implements the iterable interface. Right? Set implements the iterable interface. Right? Arrays do not technically implement the iterable interface, but the language pretends that they do. Right? So in other words, you can write a for each loop for an array. The compiler does something different compared to a list or set. Right? So if you can write for each blah in blah, then that blah implements the iterable interface. Right? So how does the iterable interface work? Well, it just returns an iterator. Right? And now the iterator does the work of looping over the interface. Right? So don't get these two interfaces confused. Right? So there's one called iterator, right? And then there's another one called iterable. Right? And the iterable interface is the thing that returns an iterator. Okay, so in Python, which I guess you didn't learn as your language, you can write a loop as follows. Right? So the syntax in Python tends to be more compact than Java. Right? But in Python, you can write every loop that you write looks like this. Right? Looks something like this. Right? It's always for I in some object. Right? There's no for int I blah 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 blah. Right? There's no C-style counting loop in Python. Right? If you want a C-style counting loop, you have to write it like this. Right? You make a range object. Right? That range object knows how to count from 0 to 9. Right? So that's what in range 0, 10 means. Right? Starts counting at 0, goes up to but not including 10. Right? So every Python loop looks like that, which is actually really nice to write. It's a lot quicker to write. It's a lot easier to read than a C-style loop. Right? So can you do the same thing in Java? Right? Java doesn't have this nice loop. Right? The closest you can get is the following. Right? So I can write a for each loop in Java that loops over a range object. Right? So I can make my own class called range that corresponds to the Python range. Right? And a range is just, I think I tell you, oh no, I don't tell you. So, right here. No, I don't tell you, sorry. So a range object the range object that I'm going to make, it's just a counter. Right? So it can start counting at 0, it goes up to but does not include 10. Right? Can't go backwards. Always counts in increments of 1. Right? You can change it to count in increments of something else, but for our purposes, it's always going to count in increments of 1. Right? So if range implements the iterable interface, then we can write this kind of loop. Right? And you never have to write a for int I equals blah 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 loop anymore. Right? Okay, so what does it look like? So I'm going to make a class called range. Right? Now range is just a counter that starts counting at some number, right, and stops counting before that number, right? So stop is the value that's 1 less than the endpoint. Sorry, stop is the value that's 1 greater than the endpoint. Right? If I want to be able to write a for each loop, the range class has to implement iterable. Right? So in other words, range has to provide an iterator object. So what do my constructors look like? The constructors should initialize start and stop, right? I would like to be able to make a range object with this one number. So I'd like to be able to write new range 10. And that makes an object that counts from 0 up to 9, right? So I have one constructor that just takes in the stopping value, right? To implement it, I just chain to the second constructor, right? Passing in 0 for the starting value, right? The second constructor takes in the start value and the stop value, right? Remember, the stop value is 1 more than the actual stop value, right? We have a little validation check here, right? So this range object always counts up, right? So if stop is less than start, that's a problem, right? So we should throw an exception. Right? Otherwise, you just set this start and this stop to equal start and stop. Okay, so because this class says it implements iterable, I need to return an iterator object somewhere, right? So I need a method called iterator, right, that returns an iterator object, right? And it's an iterator whose value is an integer, right? Because I want my range to be to count using int values. Right? So you can return an iterator that returns a value that's an integer value, right? And now I need to provide an iterator class, right? And there is no iterator class in the standard library that's suitable for our purposes, so we have to roll our own. So I'm going to return a new range iterator, right? And inside the range class is the definition of the range iterator class. Right? So we haven't seen this before. This is all brand new. Right? So inside my range class, there's going to be another class. Right? The class is private. Right? So what does that mean? That means only range objects can use this class. Right? So only a range object can actually make a range iterator object. Right? No one external to the class can make a range iterator object. It's just a class. Right? So it looks exactly the same as any other class, right? So class, range iterator, right? The iterator has to implement the iterator interface because it's an iterator, right? And this class here, range iterator, is an example of what's called a nested inner class, right? And in Java, it's normally just called an inner class. Right? So what's a nested class, right? This is a nested class, not a nested inner class, right? Inner class is something different in Java. So a nested class is a class that's defined inside of another class. Right? Range iterator is defined inside the range class. It's a nested class. Right? Oops, sorry. Right? Now, what's the purpose of a nested class? Right? So the purpose of a nested class is you want to make a class, and its only purpose is that it's serving the class that it's in for some purpose. Right? Its only purpose is to serve the class that it's in, right? So our range iterator class, right, its only purpose is to serve the range class, right? And the only reason we're making a range iterator is so that the thing can count, right? That's all it's doing. The range iterator is the thing that's going to do the counting. Right? So if you implement a nested class and you realize later on that, hey, it might be useful if someone else could use this nested class, right? Then it should be a top-level class. So in other words, it should be in its own Java source code file, and it should not be in another class. Right? Now, iterators are usually defined as nested classes because it doesn't make sense to have an iterator without having its enclosing class. Right? So in other words, it doesn't make sense to have a range iterator if there's no range object to iterate over. Right? So in other words, a range iterator can't exist on its own, right? It needs a range to loop over. So this is a perfectly valid this is a perfectly good example of when to use a nested class. And it's the same is true for list iterator. So if you look at the list class and you look at its iterator method, right? It actually returns, and you look at the source code for it, it actually returns a list iterator. The list iterator class is defined as a nested class of list. Okay, so that's a nested class, right? Now, I told you this is a nested inner class, right? So what's an inner class? right? So an inner class is a nested class that's not static. Right? It's not static. So there's also something called a static nested class. Right? So nested class is an inner class, not static. Right? Objects of an inner class type always have a reference to an object of the enclosing class. Right? So what does that mean? If you have a range iterator object, inside that range iterator object is a reference to its range. Right? So there's a reference to the range that it's looping over. An inner class object is allowed to access the fields of its enclosing class. Right, so what does that mean? It means a range iterator object is allowed to access the fields of its range. Right? So when I make the range iterator object, it's able to access start and stop. Right? Even though start and stop are private. Right? Because the class, because the inner class, because it's an inner class, right, it's allowed to look at or access start and stop. Okay, so what does the range iterator do? It doesn't do anything, it just counts. Right? That's all it literally does. Right? So a newly created range iterator object should start counting at the starting value of its range. Right? Every time next is called, right, the iterator throws an exception if the count has reached the stopping value of its range. Right? So in other words, if the iterator reaches the value stop, it can't count any further. Right? If it hasn't reached the value stop, then it just returns the next number in the range. Right? So it returns the current count and then adds 1 to the count. Right? Every time you call hasNext, it returns true if the current count is less than the stopping value. Right? So have you reached the end of the range? No, return true. Right? Have you reached the end of the range? Yes, return false. Right? So all it's doing is counting. Right? So how do you implement the range iterator class? Right? It's a counter, so it needs a value. Right? If you look at this, this is just the counter class again. Right? So it needs a value. What does the constructor do? The constructor starts the value, right, at the starting value of the range. Right? Notice the bizarre syntax that's used in the inner class. Right? So if the inner class object needs access to the range, to the outer class field, right, you use the name of the outer class dot this dot name of the field. Right? So range dot this dot start is the start value for the range object that the range iterator is looping over. Right? You have to write this. Right? You have to write range dot this dot start. Okay, what does hasNext do? Right? hasNext returns true if the current count is less than the stopping value. Right? The current count is val. Oh wait, the value returned by next. So the current count is val. Right? So if this val is less than the stopping value of the range, return true. Right? Otherwise return false. Right? Again, notice the bizarro syntax. Right? I need to access the field from the enclosing class, so I need to use the name of the enclosing class. Finally, what does next look like? Right? So next returns the next value in the iteration. Right? In other words, it returns this dot val. Right? So we're going to return result here, which is just this dot val. Right? Next also advances the iterator 1 position. Right? So it adds 1 to the current count. Right? So remember what the current value is, add 1 to the value, return the old value. Right? It also needs to throw an exception if there are no more values in the range. Right? So call hasNext, check if it returns not, false. Right? So if there is not a next element in the range, throw an exception. Right? The exception that you throw is no such element exception. Right? So that's specified by the next method in the iterator class. Right? And that's it. Right? So you've now got a counter. Oh, so you now, after doing all of that, right, you can now write code that looks like this. Right? So for int I, in the range 0 to 10, print out I, and that gives you the values 0 through 9. Right? So in other words, you can replace any of your counting loops that count by increments of 1 up using a range object. right? If you extend the range class a little bit, you can make it count down, or you can make it count in increments of some value, not 1, right? Either up or down, right? And the extensions are not difficult. The syntax is weird, but the extension is not difficult, right? I guess that's it for today. We'll look at examples of more interfaces in the next lecture. That's a fairly hard example, by the way. So that's a pretty hard example as your first interface.